Certainly, you must be acquainted with someone who is musically inclined. I too recently embarked on the journey of learning to play the piano, or more accurately, an organ, as you might recall from a previous episode. It's a fascinating endeavor and I find great enjoyment in it. Even if you are not a musician yourself or don't know any, chances are you've encountered live musical performances at events like weddings, operas, or even on the streets. The instrumentalists, not relying on vocal cords but rather their instruments, create a melodic harmony that resonates with audiences. Today, our focus is on the realm of musical instruments and the intriguing physics behind their operation. Musical instruments, deeply rooted in the principles of physics, serve the purpose of producing captivating sounds that have enriched cultures across centuries. The intricate interplay of forces, materials, and geometry contributes to the complex physics behind these instruments. Central to understanding musical instruments is the concept of sound waves. These waves, a type of mechanical wave, necessitate a medium such as air, water, or metal for propagation. Sound waves exhibit key properties. Frequency, measured in hertz, determines the pitch of a sound. Amplitude signifies intensity or volume, with larger amplitudes resulting in stronger sounds. And wavelength, inversely proportional to frequency, influences the length of the sound wave. The speed of sound depends on the properties of the medium it travels through. For instance, in dry air at room temperature, sound travels at 343 meters per second. Musical instruments set the air particles in motion, creating compression and rarefaction zones that propagate as sound waves. Human ears are sensitive to frequencies ranging from about 20 Hz to 20,000 Hz, processing these vibrations as musical notes. Vibration stands out as a fundamental concept in understanding how sound is produced in musical instruments. Whether it's the strings of a guitar or piano, membranes in percussion instruments, or the air columns in wind instruments, vibration is the primary mechanism through which sound is generated. Factors like string tension, length, thickness, and the point of string excitation influence the frequency of vibrations and, consequently, the pitch produced in stringed instruments. The concept of harmonics, higher frequency components of sound, adds to the unique tonal qualities of each instrument. Resonance, a critical aspect, occurs when an object vibrates at its natural frequency or harmonics, significantly amplifying vibrations and enhancing sound production. The design of musical instruments takes advantage of resonance to amplify vibrations efficiently. The size and shape of the instrument, along with material properties, affect resonance frequencies. For example, larger resonance chambers, as found in instruments like the double bass, produce stronger sounds. Material choices, including those for strings, contribute to tonal qualities and timbre. Musicians skillfully manipulate these physical properties to create the desired sounds. They adjust variables like string length, air column geometry, or the opening and closing of tone holes in woodwind instruments to control pitch. Furthermore, musicians control volume by varying the intensity of their playing or adjusting breath pressure in wind instruments. Exploring unconventional techniques, some musicians like Jacob Collier push the boundaries of instrument design to achieve unique sounds. In essence, the physics behind musical instruments forms a captivating subject that melds materials science with classical physics. As individuals play instruments, they actively engage with the physical properties of their chosen instrument, producing sound waves at specific frequencies and amplitudes. This understanding not only enhances appreciation for music but also contributes to advancements in instrument design and research. Don't forget to like and subscribe to Mind Blowing channel.